In the last class, I defined convex functions, and we looked at these first order conditions for convexity. Recall that we gave two different geometric interpretations of convex functions. One in this, using this particular notion that if you take any 2 points on the function, then the straight line that joins these 2 points always lies above the function itself. So that was the first geometric notion. So if this happens for every pair of points on the function, then it's said to be convex. Similarly, we saw another equivalent notion of convexity in terms of the tangent plane. So the function is convex if and only if the tangent plane always lies below the surface that the function defines, right? So these two are extremely useful notions, but when you want to really check whether a particular function is convex or not, what helps most is this second order test for convexity. The second order conditions. So basically, if f is some function, this could be defined over some convex set A, this is defined over some convex set A. If this is twice differentiable, so in other words, the Hessian exists at all points in the domain, then f is convex if and only if the Hessian evaluated at any point x is always PST. Okay, so this sort of curly greater than or equal to will be used to denote positive semi-definiteness. Okay, so it's an if and only if condition, and it has a very natural interpretation in terms of, let's say, for functions in R, right? What does this translate to? So let's restrict ourselves to functions on the real line. Then f is convex if and only if the second derivative is greater than or equal to 0 at all points. Okay? What does that mean? Like geometrically, we're just reusing the same words, convexity or concavity, but what does the second derivative actually represent physically? Yeah, so it's the rate of change of slope in some sense, right? So your function so let's take an arbitrary point at which the slope is perhaps negative. Okay, take this particular point. This is a convex function. So the slope is negative, implies that the tangent at this particular point looks something like this, right? That's bad. Right, this is what the tangent looks like. correct? So if the second derivative is greater than or equal to 0 at every point, what can you say about the slope? The slope can only increase from beyond this particular point. It can never decrease, right? Which means that, okay, right now the function is in a decreasing trend. The rate of decrease can only sort of reduce, right? So in other words, it should start gradually increasing at some point, and once it increases, it has to keep increasing. So it's never possible for the function to decrease and then increase and then decrease again. Once the function starts increasing, it can only increase, it can never decrease. Right? So that's one way of intuitively thinking about the second derivative test or the second order conditions for convexity. Right? And although I didn't explicitly point out, all of these can be extended or have their natural uh, ideas both for strict convexity. So basically, recall that a function is said to be strictly convex if f of alpha x1 plus 1 minus alpha x2 is strictly less than alpha f of x1 plus 1 minus alpha f of x2 for all points x1, x2, and alpha lying strictly between 0 and 1. Right? So in other words, the function is never flat at any point. That's one way of thinking about strictly convex functions. If you take the straight line joining any 2 points on the function, then the function value is strictly below this straight line. Kind of what happens in f of x equal to x square, but that doesn't happen for example, examples like this. Likewise, there's also the notion of the first order conditions. So f is convex if and only if f of x is strictly greater than f of x naught plus the gradient of f at x naught times x minus x naught for all x not equal to x naught. At x equal to x naught, the left hand side and the right hand side are always equal. So let me perhaps write this down here. F is strictly convex if and only if f of x is greater than f of x naught plus the gradient of f at x naught transpose x minus x naught for all x not equal to x naught. Okay. So in other words, this tangent is a strict lower bound on the function. So there is a gap, there is always at any point except the point where the tangent touches the function, there is a non-zero gap between the tangent and the function value itself. And likewise for the second order condition, it's strictly convex if and only if the Hessian is positive definite. Okay, so all of these are kind of natural notions. Any questions so far?
Entries of the Hessian matrix being positive always.
That's not enough.
So that's a weaker condition.
It's not necessary or sufficient for it to be PSD or positive definite, right? For example, you can have a diagonal matrix with all, let's say, the identity matrix. This is a positive definite matrix, but all the non-diagonal entries are 0. Likewise, you can easily construct examples of matrices where all of the entries are non-zero, but it's not positive semi-definite. So entry-wise being 0 or non-zero doesn't imply positive definiteness or semi-definiteness, and vice versa. There are other conditions that you can give. For example, so there's this notion of diagonal dominance and so on. But let's not get into that. But in general, non-negativity of the entries does not imply positive semi-definiteness. Any other questions? Okay, since one of you asked this in a previous class, there's also a notion of strong convexity, which is different from strict convexity. In fact, it's a stronger notion than strict convexity. So strict convexity basically tells you that, for instance, the straight line joining these 2 points is strictly above the function itself. Right? Strong convexity, in a sense, tries to quantify by how much is it guaranteed to be above the function value. But sort of a more natural way of thinking about it is the following. So the more natural way is to think about it in terms of the first order condition. So the first order Taylor series expansion. So the first order condition says that for a function to be convex, the function should lie strictly above the tangent. And by how much should it be above the tangent? That is characterized by strong convexity. So we'll say that a function, let's say Rn to R, is sigma strongly convex if, again, it's a very natural notion, f of x is greater than or equal to f of x naught plus the gradient of f at x naught transpose x minus x naught, plus, essentially you think of it in terms of the second order Taylor series expansion, plus sigma by 2 times norm of x minus x naught square. Okay. And here we're assuming that sigma is some parameter which is strictly greater than 0. If you set sigma equal to 0, then you just get convexity, right? Because if you set sigma equal to 0, then it just says that f of x should be greater than or equal to f of x naught plus gradient of f at x naught transpose x minus x naught, which was a condition for the standard convexity. But this gives you something slightly more if sigma is greater than 0. And as it so happens, to analyze the performance or running time of certain convex optimization algorithms, you need this notion of strong convexity. Effectively, the rate of convergence of many convex optimization algorithms to the minimum is this rate depends on the value of sigma. So larger the sigma, essentially the faster you might be able to converge to the local minimum. All right. So sigma being large effectively says, I mean, if you think about it, think about what this quantity means, right? Let's look at f of, I'll just rearrange these terms, f of x minus f of x naught plus gradient f x naught transpose x minus x naught should be greater than or equal to sigma by 2 times norm of x minus x naught square. So let's suppose that I have some function that looks like this and take the tangent to this particular function at some point. Let's suppose that this is my x naught. Then how far, so this is the function value, which is essentially the y value at this particular point, whereas this is the y value for the tangent, effectively this quantity, right? So the quantity on the left hand side is essentially how far away is the function from the tangent at x. So this is my x naught, this is x, this particular gap is the left hand side, and the right hand side is some constant times norm of x minus x naught the whole square. So if x is farther away from x naught, then essentially this gap is increasing at a quadratic rate, correct? So by what rate does this increase? It increases at a rate of sigma.
What the whole domain can be at some places strictly convex, and at some places can it be strongly convex? Because essentially it's the distance with the tangent line what defines
Potentially, so if it is strongly convex, it is guaranteed to be strictly convex.
There will be some domain where it's sometimes strictly convex, not strongly convex, because the shape doesn't change.
The shape doesn't include, so in fact there can be certain regions where the function is not strictly convex, but in certain regions it is strongly convex. You can cook up very simple examples. For instance, you just take the quadratic function. The quadratic function is strongly convex, right? But let's say I clip, let's say the bottom part of this quadratic to make it flat, right? So something of the form, say f of x equal to x square for mod x, let's say greater than or equal to 1, and maybe equal to 1 for mod x less than or equal to 1. This function is convex, but for all x such that mod x is greater than or equal, mod x is greater than 1, this is strongly convex, whereas for x between -1 and +1, this function is not even strictly convex. So if a function is sigma strongly convex, if sigma is large, then it means that the function is kind of more sharp, right? So in other words, it's steep in some sense. And the larger the value of sigma, the more steeper the valley looks like, right? So this would be for one value of sigma. If if you have a larger value of sigma, the same function would look potentially something like this. Okay. Now, if you take an algorithm that behaves something like gradient descent, then if you take any point, and let us say you move in some direction, let's say in the direction of the negative gradient by some amount delta, then it's just visually you see that the function value decreases at a faster rate. So there is a high chance of finding the local minimum or finding the minimum much faster if sigma is large. That's why strong convexity is a helpful notion.
Convex implies strong convex.
No, not necessarily. So this, for it to be strongly convex, this sigma is something that doesn't depend on x or x naught. Correct? On the other hand, strict convexity just implies that this left hand side is strictly greater than 0. You can't. So at some point sigma may be close to 0, arbitrarily close to 0.
And about the delta, you can modify your delta to.
Which one?
If you have something with a smaller sigma, you can increase the value of your step.
You can increase the value of your step. I agree, but we're looking at, let's say, for a fixed delta. For the same value of delta, the function value decreases much faster. Okay. Again, we're looking at a specific, I've not even defined what class of algorithms I'm talking about. But intuitively, it feels that you should be able to find, because it's steep, taking small steps. If you let's say you fix a particular value of delta, you should be able to reach the minimum using fewer number of steps than when compared to for something where sigma is large. Yeah.
For that, when you're taking one function is strongly convex, what do you say that the third derivative exists as well? Because the second derivative.
No. You can't say the third derivative exists. That is not guaranteed.
If the second derivative exists, and it's constant. Then
It is not constant.
if it's constant.
But then you're automatically making a very strong, if the second derivative exists and it is constant in some sense, so in other words, the Hessian does not depend on x, right? Then effectively it's a quadratic. Okay. Existence of first and second derivatives doesn't imply existence of third derivative in any case. Oh, if it is strong, if it is sigma strongly convex for some sigma greater than 0, then it is automatically strictly convex, because this right hand side is strictly greater than 0 for every x naught equal to x naught. But the reverse is not true. Just because it is strictly convex doesn't imply strong convexity. For example, maybe another way to think about it is, maybe this f of x minus this particular quantity could maybe be greater than or equal to some function of x minus x naught, but not x minus x naught the whole square. Something that's slower than x minus x naught the whole square. Okay, that's one sort of condition. Again, I'm being very loose here. Okay. We're talking about multivariate functions here. So x naught are all vectors. Right? But of course, we're dealing with functions in the sense that it's a function from Rn to R. That's going to be what we will focus on for the whole course, pretty much. The codomain is always going to be R, nothing else. Which one? It's a definition. If you want to use norm instead of norm squared, then you get something else, but we won't call it sigma strongly convex. Also, something to keep in mind that you could potentially, I just called it norm. This may or may not be the L2 norm. So when you say sigma strongly convex, typically it is with respect to some particular norm. Even though you're in Rn, you could want to define sigma strongly convex with respect to the 2 norm or the 1 norm or the 3 norm or something else. Okay. But typically when I talk about sigma strongly convex, it will usually be with respect to the 2 norm, the L2 norm. Any questions? Okay, so this is more of an aside. We may revisit strong convexity at a later point when I talk about some convex optimization algorithms. But it's a useful idea to know, and it's good to know that strictly convex does not imply strongly convex. Okay. For every x naught, this should hold for every x and every x naught. Okay, so let's quickly do some examples of functions which may or may not be convex. More basic, right? So let's look at f of x equal to log x to the base e. This is concave. How do you prove that it is concave? Okay, what is the second derivative equal to? So d square f by dx square. Again, this is defined only for x greater than 0. So the domain is the set of positive real numbers. What is the second derivative equal to? It's minus 1 by x square, which is strictly greater than 0 for, this is strictly less than 0 for x greater than 0. So it is concave. Right. Let's take something a little more interesting. So let's say norm, the L2 norm square. Okay, the claim is that the 2 norm squared of x is convex, and why?
Because the double definition would get that the 2i is basically I forgot.
This is a vector valued function.
So Hessian matrix is 2i.
The Hessian matrix is 2 times, it's not the Jacobian.
If you apply Jacobian, it becomes 2x transpose, and Argand gradient will become 2.
Yes. So this is equal to 2 times the identity matrix. So it's a diagonal matrix with all entries equal to 2. And this is, it is positive definite, because what are the eigenvalues of 2i? 2 repeated n times. So this is positive definite and therefore strictly convex. Okay, let's take f of x equal to, again, f from R to R, f of x equal to mod x. Okay, why? It's not, why is it's not affine, right? The claim is that this is a convex function. Why is this a convex? You have to prove that whether it's a convex function or not. Double derivative is 0. Okay, so let's take f of x equal to minus mod x. Double derivative is also 0 at all points except 0.
Which are two half planes?
I don't quite understand.
This intersection.
What do you mean intersection? It's not an intersection, right? It's not a set.
The region.
The derivative is sort of that is increasing.
So it's not differentiable at all points, right? Okay, so then I could say let's take the following function f of x equal to minus x for x less than 0 and say x plus 1 for x greater than 0, less than or equal to 0. Is this convex? It has the same first derivatives as f of x equal to mod x. Mod x is continuous, okay. Again, the derivative does not exist at all points. That's the whole thing.
So its double derivative is 0 and it has a
The double derivative is 0. Where is the double derivative? Okay.
the first definition double derivative is 0 and
How did you conclude that it has a minimum? Yeah, visually, you could say that true, but that's not. Is it plus 1 or minus 1? Yeah, you have a point.
first definition and triangular inequality.
Okay, let's use the first basic definition. So the first derivative, second derivative tests work only if the first and second derivatives exist at all points. Otherwise, you cannot conclude anything about convexity. Right? That's a fundamental requirement. Those derivatives have to exist at all points. But let's try to go back to the definition of convexity. What I need to show is that f of alpha x1 plus 1 minus alpha x2 for any pair x1, x2, and for any alpha between 0 and 1, this should be less than or equal to alpha f of x1 plus 1 minus alpha f of x2. But what is this equal to? This is nothing but mod alpha x1 plus 1 minus alpha x2, correct? Just by, in this case, you just use the fact that mod x plus y is less than or equal to mod x plus mod y. So this is mod alpha x1 plus mod 1 minus alpha x2. Alpha and 1 minus alpha are between 0 and 1, so they're all non-negative quantities. This is equal to alpha times mod x1 plus 1 minus alpha times mod x2, which is alpha f of x1 plus 1 minus alpha f of x2. Hence, now you can conclude that the function is convex. In fact, you can use this approach to conclude that any norm is convex. The same idea applies. So if you take f of x equal to norm x, then effectively it's norm of alpha x1 plus 1 minus alpha x2, which is just by the triangle inequality is less than or equal to norm alpha x1 plus norm of 1 minus alpha x2, and the rest follows exactly. All right. Maybe coming back to, I think an idea that one of you had, sort of, if you have some sort of a function that is constructed using piecewise affine functions, is the resulting function convex, right? So let's try to see it visually. Okay, I'll leave the actual proof as an exercise for now, but let's take 3 lines. Right, 3 straight lines. This is line 1. I take another line, let's say line 2, and another, let's say line 3. Then visually you can see that this right, this particular function over here this function is convex visually. Okay, so what I want you to show is that, let's have a bunch of vectors ai and bi. Ak, b1 through bk. Then f of x equal to max overall I from 1 up to k, ai transpose x plus bi. This is convex. So remember that this sort of function that I constructed as using which is a composition of piecewise pieces of different lines. In this region, this, if I call this f1, if I call this f2, if I call this f3, and at every point f is nothing but max of f1, f2, f3. Right? So in this region, this green line is above the blue and the pink lines. In this region, this blue line is above the green and the pink lines. And in this region, the pink line is above the blue and the green lines. In fact, let me maybe give something a little simpler. You can first start by showing the following, that f of x equal to max over I of xi is convex. Okay, so basically this is the function that just picks out the largest component of the vector at any point. Second, try to prove that if f is convex, then f of ax plus b, so any affine composition of a convex function with an affine function is also convex. The intuitive way of thinking about this is that an affine, so what does an affine transformation do? It just rotates and shifts the coordinates, nothing more than that, right? So in some sense, the shape, the fundamental shape of the function is still preserved, even if you compose it with an affine transformation. At best, you're just going to be sort of rotating and perhaps stretching the function or the surface in different directions. So convexity still gets preserved.
What is that Ax plus b? That argument is convex. Convex of convex.
We will come to that a little later. So how compositions can behave with respect to each other. But try to think about it anyway, because, okay, so one suggestion is to think about convexity. So one way of testing convexity is using the second derivative test, right? So just take the composition of two functions f and g, and you can compute the second derivative, for example, using the chain rule, and see if it is guaranteed that if f and g are both convex. Try to see if it is always true that the second derivative of f of g is also convex. You'll see that that's not the case. You need one additional condition. Try to think about what that condition should be. So the question is, if f and g are both convex, is h of x defined to be f of g of x convex? Now you can think of this more general. So right now we'll just assume that g could be a function from Rn to R, but f is a function from R to R. Okay. So you can assume that the first and second derivatives of both functions exist. Whatever. In this case, the second derivative of f and the Hessian of g exist. Just to keep it simple, just assume that f and g are both functions from R to R. And likewise, it is not necessary for f and g to be convex for f of g of x to be convex. So far we've essentially assumed that we've seen sort of two conditions. One, wherein the function is reasonably smooth, first and second derivatives exist, and we have these nice geometric interpretations. But as we've just seen, there can be some examples where the function is not differentiable at all points. The gradient may not exist, and there are many algorithms, as we'll see later, which depend on, which require the notion of a gradient. Okay, so should we just lose hope if the function is not differentiable? Because just the functions that we've seen over here, for example, this is a function for which the derivative or the gradient need not exist at all points. There are many points where the gradient does not exist. Right here, just visually, if you look at it, at these 2 points, the derivative does not exist. Right? Similarly, if you take f of x equal to norm of x, any norm, the derivative does not exist at x equal to 0. The gradient does not exist at x equal to 0. So can we not use any versions of the first or the second derivative tests? As it turns out, we can. There is an equivalent notion of the sort of first derivative test, not test I should say, but a characterization, even if the function is not differentiable. So effectively, what does the first derivative characterization tell us? If a function is convex, then the tangent is always a lower bound for the function, right? So let's take the example that we saw earlier, which is f of x equal to mod x. Right? So what happens at any point where which is not x equal to 0, the tangent exists, right? In fact, it is equal to this on the right hand side. For x greater than 0, this itself is the tangent at any point. And for x less than 0, this itself is a tangent at every point. But what about x equal to 0? What happens? Is it that a tangent doesn't exist? No unique tangent exists, but there are multiple tangents. And in this case, every tangent satisfies that property that we had earlier. Right? The tangent always lies, every tangent lies below the function. Right? And in many cases, the slope of any of these tangents can be used for the algorithms in place of the gradient. Okay. Is that a tangent? Yeah. So you're right. How do you define this notion of a tangent?
It's a discontinuous.
It's not discontinuous, right? This is not discontinuous.
Not differential point is continuous.
Correct.
Not an end direction.
So let me make my statements a little more precise. That will clarify the point that you have. Right? So I'll define this notion of a subgradient. So suppose I have a function from Rn to R. We'll say that a vector v in Rn is a subgradient of f at some point x0 if f of x is greater than or equal to f of x0 plus v transpose x minus x0. So this is nothing but the straight line that passes through x0 and has slope v, or basically has normal vector v. All right, and this happens for all x belongs to Rn. So a vector is a subgradient if it defines a tangent that is a lower bound for the entire function. The subgradient may not be unique. There could be multiple subgradients at a given point. I mean, case in point, for this particular function mod x, there exist infinitely many subgradients at x equal to 0. But there exists only one subgradient at x greater than 0, at any point x which is greater than 0, and or at any point x which is less than 0. Right? So the set of all subgradients at x naught is denoted this nabla f of x naught. So we'll use this particular notation to denote the set of all subgradients of f at x naught. So for example, if you take f of x equal to norm x, depending on whether you are looking at the L2 norm or the L1 norm or L3 norm or anything else, there could exist infinitely many subgradients at x equal to 0. Okay. But you should also note that the set of all subgradients could be empty for an arbitrary function. For example, let's take the following function. Some function that looks like this. Let us take this particular point over here. Is it possible to draw a straight line that passes through this particular point such that the straight line is below the function everywhere? It's not possible, right? So the subgradient need not exist at all points for an arbitrary function. So it's possible that no subgradient exists. It's possible that a unique subgradient exists. In fact, if the gradient of f exists at x naught, then okay, with a little more caveat, exists and f is convex, then there exists a unique subgradient and it's equal to the gradient itself. Okay, so it's possible that no subgradient exists, possible that the subgradient is unique. It's also possible that there are infinitely many subgradients. Okay. Whatever. But the nice feature about convex functions is that if the function is convex, then at least one subgradient exists at all points, right? And this holds whether the gradient exists or not. Okay, it's not clear why this is true. And you have to be careful because, as we just saw, there are examples where the subgradient need not exist. But we know that if the function f is convex and the gradient exists, then the subgradient exists. Because we just proved that first order conditions for convexity.
This is the opposite direction.
Which
You can observe subgradients for non-differentiable functions. This follows convex.
That's true. So you mean to say that at every point, if the subgradient exists, then the function is convex. True. Yes, that also holds. That's another characterization of convexity. Right, but at this point I'll only restrict myself to this sort of weaker condition, which is I won't give a full proof, but I'll at least give a high level justification as to why this is true, why a subgradient must exist at all points, and that involves some other nice ideas that we'll use in many other places later on. Okay, so we'll briefly take a detour from convex functions back to convex sets, right? And define these very interesting notions of what is called a separating hyperplane for sets and a supporting hyperplane for sets. Right, remember that a hyperplane is nothing but set of all points that satisfy A transpose X equal to B. Correct? So we'll say, so effectively every hyperplane can be defined using a vector A and a number B. Right? So A represents the direction. In other words, A represents the vector that is normal to the hyperplane, and B represents how much you shift from 0. If B is equal to 0, then the hyperplane is nothing but the null space of the vector A, the matrix with only the vector A, and therefore B represents how much you shift away from 0. So let me define a hyperplane being defined by two parameters, A and B, where A represents the normal vector and B represents the constant shift. We'll say that this separates two sets or two subsets of Rn, A and A prime, if the most natural way of defining it. If the entire A lies on one side of the hyperplane and A prime lies on the other side of the hyperplane. So A transpose X is, say, greater than or equal to B for all X in A, and A transpose X is less than or equal to B for all X in A prime. Okay, so note that I'm allowing A and A prime to sort of intersect along the plane. That is allowed. Okay. Similarly, there's a notion of strict separation. So it strictly separates A and A prime if these are strict inequalities. So this is a pretty intuitive. If I take two sets, if this is my set A and this is my set A prime, I can construct a hyperplane that separates A and A prime. But then it's also possible to construct A and A prime where no separating hyperplane exists. For example, let's say that my set A looks something like this, and my set A prime looks something like this. This is my A prime, and this is my set A. Visually, you see that there is no way of constructing a separating hyperplane for these two sets. In fact, can get more extreme. So for example, my A could be something like a disk, and my A prime could be another set that lies inside this. This is my A prime, this is my set A. So it's very easy to construct sets that cannot be separated by a hyperplane. The nice fact is that if A and A prime are convex, then there will always be at least one separating hyperplane. So as long as A and A prime are convex, you will always be able to find a separating hyperplane. I won't prove this particular theorem, but you can take a look at the book by Boyd that has a simple proof for this particular theorem.
If one is a proper subset of the other?
Okay, very good point. So if A and A prime are convex and non-intersecting, that's a good point. I should have explicitly mentioned that. Whenever I'm talking about separation, I will imply that A and A prime are disjoint.
Just to be clear, A prime is not complement of A.
It's okay even if it is the complement of A, because as I said, it separates A and A prime, so they're allowed to intersect at the boundary. Right? Of course, I want both A and A prime to be convex. It's not enough if only A is convex. So I agree, if you take a set A, a convex set A, and you look at its complement, potentially a complement need not be convex, right? Because it could include everything around A. But for instance, if I take say a half space is convex, right? The complement is another half space which is also convex, and there exists the hyperplane that defines this half space is itself a separating hyperplane that separates A and A complement.
Complement of a half space does not have this boundary.
Which one?
A half space.
That's okay. So I don't restrict A and A prime to be closed. It's okay if they're open also. The only requirement I have is that the intersection be empty. That's it. Okay, and also I have this sort of weak requirement that A transpose X should only be greater than or equal to B for all X in A, and A transpose X be less than or equal to B for all X in A prime. So this is a useful notion, but another useful notion is the notion of a supporting hyperplane, which kind of mimics what a tangent does for functions, right? So we say that a hyperplane defined by a normal vector A and a number B is a supporting hyperplane that passes through some point x naught. Typically we take x naught to be on the boundary of a set A. So it's a supporting hyperplane for a set A that passes through x naught that belongs to the boundary of A. If it satisfies the two conditions, that is, one, the entire set A lies on one side of the hyperplane, or in one half space defined by the hyperplane. And second, the hyperplane passes through x naught as required. So A transpose x naught should be equal to B. So let's say that I have some set A. This is my set A. Geometrically, what would a supporting hyperplane, let me take some point over here. Okay, this is my point x naught. What does a supporting hyperplane for A at x naught look like? It's basically going to be a line that is tangential to the set A. Right, so this is a supporting hyperplane, but something else that maybe does not, this is not a supporting hyperplane. All right. And once again, a supporting hyperplane need not exist for all sets, for arbitrary sets. For example, if I take a set that looks like this, do you think it is possible to construct a supporting hyperplane at, say, this particular point? You can't. So a supporting hyperplane may or may not exist for an arbitrary set A. But again, convexity helps. If the set A is convex, then a supporting hyperplane exists at every point on its boundary. So if A is convex, then there exists supporting hyperplane at every point on the boundary.
This is regardless of differentiability.
There are no functions, right? We're only talking about sets.
You want to say basically take the region above convex.
That's exactly what I will do, right? To show the existence of a subgradient.
This is
Which one? The supporting hyperplane theorem. In a sense, the supporting hyperplane theorem follows from the hyperplane separation theorem. We just take one point, all right, which is x naught, that is one set, okay, and you take the entire interior of the set A, put it in another set. Now these two are both convex sets, therefore there exists and these don't intersect with each other, therefore you can find a separating hyperplane, and this separating hyperplane will in fact be the supporting hyperplane. That's the idea. Of course, I have not proved the hyperplane separation theorem, but again, you can look it up. It's there on Boyd. I just want to skip this in the interest of time. Question? All right, so exactly as you suggested, I want to use all of these ideas to firstly show that a subgradient exists at all points for a convex function. Okay. So for a convex function, I'll define two sort of sets, two different types of sets. So we'll go back to convex functions now. So suppose I have a function from, say, Rn to R, or in general any vector space to R. I'll define two sets. The first set is the so-called alpha sublevel set, which is whatever, let me call it S alpha of F. This is simply the set of all x in Rn such that f of x is less than or equal to alpha. Okay. if f is convex, then S alpha of x is also guaranteed to be convex. Right. So what does this mean? It's basically, let's say I have a function. Perhaps let's take something that is non-convex, and I fix a particular value of alpha, which is essentially a particular y value. All right, let me fix this to be my alpha. So S alpha is basically the set of all values of x such that f of x is less than or equal to alpha. So that would correspond to the union of this set and this particular set. So these two put together give me S alpha. So as you can see, if the function is non-convex, then potentially the alpha sublevel set, there could be an alpha sublevel set which is non-convex. But it's not true that just because all the alpha sublevel sets are convex, f has to be convex. All right. Simple example, you take any, say, increasing function, convex or not. The S alpha will always be an interval, a half open interval, which is always going to be convex. Right? So the reverse is not true. Perhaps for us, the more relevant set is the epigraph, which is now a set in n+1 dimensions, x, comma t, in Rn cross R, such that f of x is less than or equal to t. So for a given function, what does the epigraph look like? Geometrically, what does the epigraph correspond to? So just translating this, let's say for a function f from R to R, this is nothing but the set of all x comma y such that y is greater than or equal to f of x. Correct? So what does that correspond to geometrically? Is the entire region above this curve that defines the function. Right? So this entire region defines the epigraph. So again, the first claim is that, well, in this case, I can make a slightly stronger statement. F is convex if and only if epigraph of x is convex. It requires a proof. Okay, but let's use this as a fact for now. Now, given f, which is convex, we know that the epigraph is guaranteed to be convex. It's a convex set. What does the supporting hyperplane theorem tell us? It says that there exists a supporting hyperplane at every point on the boundary of the epigraph. Right, so there exists a supporting hyperplane H AB at any point for every point on the boundary, or in other words, for every x. The boundary of the epigraph of f, or in other words, this is the same as for every x naught comma f of x naught. So every point on the boundary of the epigraph is nothing but every point on the function on the surface that defines the function, which is nothing but x naught comma f of x naught. And what is a supporting hyperplane at x naught comma f of x naught? That essentially defines the tangent plane, and that is now guaranteed to be a sort of a lower bound for the function itself. I'm sort of hand waving things a little bit over here, but that's the basic idea. All right, and this normal vector is essentially going to be the subgradient. Right, so this is sort of formal justification for the existence of a subgradient at every point on at every point x in the domain. As long as the function is convex, a subgradient exists. And for a given function or for a given set, the supporting hyperplane may or may not be unique, and likewise the subgradient may or may not be unique. But as long as f is convex, there will exist at least one subgradient and therefore at least one supporting hyperplane. All right, any questions? Okay, let's stop here.